So the new value of x is going to be equal to the previous value of x minus, because we've got to go down the hill, minus our step multiplier times the slope, times the gradient. And remember, this is the value of the slope at the previous value of x. So what we're doing here is we're taking a step that's proportional to the negative of the gradient of the function at the point that we're at. And then we're subtracting from the previous x value because we want to move against the gradient towards the minimum. And this is where the learning in machine learning takes place. So this loop is going to run 30 times. And after it's finished, let's print out our results. So I'm going to say the local minimum occurs at what? Well, the new value of x, right? Because that's what we're updating in our for loop. And we're going to print out the slope, yeah? So we just have to make sure our slope is close to 0, right? Or the value of dff of x, yeah, at, at this point. So this is going to be our derivative function, and as an input, it's going to get the latest value of x. Finally, we're going to print out what the cost is at this point. So this is the f of x value, or cost, at this point is, and this is going to be our cost function at the point where the cost is lowest. Now, before I run this, make sure you've got a plus sign here, because if you ever have to go to restart and run all, or run all above, yeah, then you may want to make sure that this loop doesn't continue going. I just caught myself out there. So I'm going to press Shift-Enter now here, and I get my print statements shooting off the results of our gradient descent. So what can we learn from this? What can we deduce from the values that we're seeing here? Well, the first thing is that we can see that they're approximations, right? This isn't an exact value. We're not getting a very clean answer here. But that might be the case because maybe we haven't run our loop often enough. So if I increase the value here from, say, 30 to 50, let's see what happens with our values that we get printed out. So one thing that we're seeing is that our slope is getting a lot closer to 0 here than before. The second thing is that this value here on f of x is also getting a lot more precise. And so is our new value of x. So it's getting much, much closer to a minus 0.5. Yeah? If I run this 500 times, let's see what happens. So as you can see, we're converging on this local minimum by brute force, right? We didn't solve our cost function here analytically. What we're doing is we're iterating and going down that valley, that cost function, until we reach the minimum point. And at the minimum, our slope is equal to 0, our cost is equal to 0.75, and this is when the x is equal to minus 0.5. So obviously you can run this thing 1,000 times or what have you, right? But oftentimes you actually know ahead of time how precise a calculation you need, right? From a resource management point of view, what you can actually do is you can tell the loop to stop running once a certain level of precision is met. And I'm sure you're looking up, yeah, you're scrolling up and you're looking at this while loop here and you're thinking, yeah, the while loop seems ideal for this, right? We can run the while loop as long as our calculation is within a certain level of precision. And you'd be right. That's exactly something you could implement if you wanted to with the structure of the while loop. Let me show you how to do this with the for loop as well. We're going to modify our code here a little bit to include a cutoff point for a certain level of precision. And the way I'm going to do this is by adding another variable up top. I'm going to say precision is going to be equal to 0.0001. Yeah, so this is how precise I want my answer to be. Now, where does this come into play? Well, what we're interested in with our precision estimate is what's the difference between the new x and the old x, right? So if those two are getting closer and closer and closer together, then our calculation is getting much more precise. So what we can do is we can say, well, the step size, yeah, is going to be the difference between our new x minus our previous x. Yeah, that's going to be the step size. And just to make sure that step size is always a positive number, we're going to say, well, what we care about is actually the absolute value of our step size. And no, change the number of times this loop runs to maybe 10. Yeah, and I'm going to print out the step size just so we can see how it evolves over time as the loop runs. So let me run this. Let me press Shift Enter here. And we can see here our step size initially starts out with 0.7 and then it decreases, right? The new x and the old x are getting closer and closer together. So we can see here our step size is decreasing. So I'm going to comment out this print statement so it doesn't execute anymore. And I'm going to add the condition for terminating this for loop. Yeah, I'm going to say, well, if the step size is smaller than the precision, so in other words, if the difference between the new x and the previous x is smaller than 0.0001, then we can terminate our loop. Then we can stop with our calculations. So put a colon there, and then the Python keyword for stopping this loop is called break. So I'm going to leave it at that. And I'm going to say, well, run 500 times. Yeah, for loop, run from 0 to 500. But if the step size is smaller than our predetermined precision, then stop running. Let's see how often our loop runs according to this logic. Well, we don't know, right? Could have run any number of times. We probably have to print the value of n. So print loop ran this many times. Forgot the S. So given these constraints, our loop ran 40 times. Yeah, it's actually not that much, not that many times. If we add an extra 0 here on the precision that we're looking for and press Shift Enter again, we can see that it ran 50 times. So it actually never gets up to 500. Yeah, doesn't go up all that way. And that's because it reaches that terminating condition, this break statement, a lot sooner. But still, the way we wrote this code, we have two conditions where it can stop. It can either reach 500 and it will stop there, or when it reaches the minimum and that step size becomes very, very, very small, then it can also terminate. Now, running the Python loop and calculating the minimum is very well and good, but I'm a very, very visual person, and I'm sure you might be too, so I find graphing things very, very helpful. The way we're going to go about graphing it is, first off, we have to kind of keep track of all the values that we've calculated inside of our loop. So we're going to create two lists, yeah, two Python lists. One of them is going to hold on to our x values. So it's going to be a list, and it's going to contain the new x values. And the other thing is I'm going to also create a list for all the slopes. So I'm going to call this slope list, and it's going to contain whatever value our derivative has at this x position. Yeah. Now within our loop, we're actually doing these calculations anyhow. So all we need to do is we need to append the x values and the slope values to our list. So I'm going to say x list dot append to add a new value to it of the new x value. And this is the x value that we've updated after we've taken our step down the cost function. So we're going to append this value to our list, and also for our slope list, we're going to append the output from our derivative function at the new x value. Yeah? And that's it. That gives us the basis for plotting our charts. So let's do that now. I'm going to go up here, and I'm actually going to copy this cell here. I'm going to go to Edit, Copy Cell, and I'm going to reuse it down here, a lot of this code. So I'm going to paste the cell above, and I'm going to edit my comment to say that we're going to superimpose the gradient descent calculations, yeah? So this is the goal. Now, we've got our two charts, and what we're going to do is we're going to add a scatter plot on top of these with the data that we've captured from our loop. Here's how we're going to do it. For our first chart, we're going to say plt.scatter, parentheses, and then we have to supply some arguments. So on the x-axis is going to be our list of x values. And for our y-axis, we want to feed our list of values into our cost function, right? So this is our f of x. Now, you might think I can actually just put the x list in here and press Shift-Enter. But this isn't going to work. We're going to get an error, yeah? And this is because our function, the way that we've written it, cannot process a list. It's unable to process this list as it is. So I'm going to have to do a little type conversion first. So I'm going to create a variable called values and set it equal to a NumPy array, which is going to take as an argument our list of x values. So our function can work with an array, but it can't work with a list. And if we press Shift-Enter, we should see that now we have a little scatter plot on top of our graph. But in terms of data visualization, that was very, very poor, right? So I'm going to say the color of these dots should be red. They should be a lot larger, so I'm going to set the size equal to maybe 100, and I'm going to give them a little bit of transparency. So I'm going to say the alpha should be equal to maybe 0.6. See how that looks. So this is looking a lot better, yeah? So we can see here, as our algorithm runs, going closer and closer to this minimum. But we can also show this on our second chart as well, right? So we can see how we're inching closer to where the slope is 0 on this right-hand chart. And we can do that by making use of the other list that we've captured. So in this case, it is a little bit simpler because we just have to write plt scatter parentheses x list, x values still the same, but for the y values, we've done a bit of a calculation already, so we can say slope underscore list. Yeah? And let's also make it a red color. Make the dots big, size 100, and alpha maybe 0.5 or something. Let's see how it goes. Yeah, it's looking not bad. But I do wonder if there maybe should be some transparency on the line itself. So if this thing had an alpha of, say, 0.6, would it look a bit better? Yeah. This looks better. Let's do the same thing with our plot at the top as well. Let's give this an alpha of 0.6 as well. Let's see. Or 0.7 perhaps. Or 0.8. Let's try. Yeah, this is looking pretty good. So we can see here that now we have our scatter plot superimposed on our derivative function, and it stops when the slope is equal to 0. And on the regular cost function, we're moving down and down and down and down into the minimum at the bottom of this parabola. You know, the cool thing is that we can even zoom in a little bit. Yeah, we can even do a little close-up of our slope. Let me show you what I mean. So if I take this bit of code here, copy it, and paste it, and say chart number 3, and call this derivative close-up, and then I change the title and say gradient descent close-up. Might get rid of the Y label, don't need that. I'm going to keep the grid, but I'm going to change what's on the axes. I'm going to go from, say, 0.55 to minus 0.2. So zooming in here on the x-axis, and on the y-axis I'm going to do the same. I'm going to zoom in from 0.3 to 0.8. I'm still going to leave it sky blue. I'm going to change the line width to 6, alpha 0.8. Just change these values around a little bit to make it a bit more distinct. Yeah, make the dots a little bigger. And if I press Shift Enter now, then nothing will happen because I need to adjust my subplot, right? I'm adding a third plot here, so I have to make sure that I have, in this case, what, 3 columns, right? I've got 3 charts. This is chart number 3 of the lot, and this is going to be also edited to chart number 2, right? On the 3-column subplot. And same with this. This is chart number 1 on the 3-column subplot. And it's now that I can run this, see what happens. Aha. So I'd say this is pretty good, right? So we've got a close-up here where we can actually watch the gradient descent converge upon that 0 value. And you can see those steps getting smaller and smaller and smaller and smaller as we're getting closer to our goal. I think this is incredibly cool. The charts look a little bit squished. Maybe what I'll do is I'll change this from 15 to, I don't know, 20 on the width. See if that helps. Yeah, that definitely looks a little better. Okay, brilliant. We've done quite a lot of work in this lesson. This has been a long and difficult lesson, but writing the code definitely helps us play around with the gradient descent. Yeah, because what we can do now is we can change a couple of these values and see how it behaves differently. So, for example, if instead of at 3, we start at -3 with our gradient descent, let's take a look here. If our starting value is -3, and I rerun the loop and rerun all the calculations and rerun the graphs, then we can see how the gradient descent comes in from the other side. So in this case, it's from the bottom here instead of from the top. So this is really, really cool in being able to actually play with the algorithm. And this is the advantage of writing all the code out and actually running it and rerunning it to see how differently it behaves. Because not only can we change the starting point, but we can also change, say, how many steps we're taking, right? So if we rerun our algorithm to only run about 10 times instead of the usual amount, then we can see how we're not getting that close to the minimum, right? So we should be getting about here, but we're actually not reaching it. So yeah, I think this is really, really cool. And in the next couple of lessons, we're going to be exploring a couple more of the idiosyncrasies and the strengths and weaknesses of this algorithm now that we've written it and graphed it. I'll see you there.